Hello everyone. Before we dive into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription really makes a difference and helps this channel grow. If you enjoy our content and don't want to miss our upcoming videos, subscribe to the channel and activate the bell to receive all notifications. Have you ever imagined that what we know as space and time is only a tiny part of a larger universe? A hidden realm of invisible dimensions that escape our senses yet shape everything? The idea might seem like a science fiction dream, but it's actually a fascinating scientific possibility that has captured the attention of theoretical physicists for decades. At the heart of this vision lies one of the most elegant and mysterious theories ever conceived, string theory. It all began almost a century ago, in the 1920s, when quantum physics and special relativity were unified in a single theoretical framework known as quantum field theory, a revolutionary step that allowed fundamental particles to be described as quanta of excitation of a field. In the 1930s, the discovery of an increasing number of particles, beyond the familiar electrons, protons, and neutrons, pushed physicists to seek logic in this new and chaotic subatomic landscape. Unstable and short-lived particles emerged, and to describe their interactions, Feynman diagrams were introduced, graphical representations that show how particles collide, transform, and separate, with each process described by an amplitude of probability whose square magnitude determines the probability of the event itself. But as energies increased in the accelerators and the strength of nuclear interactions intensified, even these diagrams began to reveal their limitations. The interactions became too intricate and elusive to be satisfactorily captured. Thus, in the 1960s, physicists began to search for an alternative. It was in 1968 that the Italian physicist Gabriele Veneziano discovered a surprising mathematical formula, initially intended to describe strong interactions, which seemed to reveal an even deeper and more mysterious structure. This marked the birth of string theory, although at the time few understood its potential. The theory received new impetus in 1970 thanks to the work of Yoichiro Nambu, Holger Bech-Nielsen, and Leonard Susskind, who gave it a more concrete form. Then, in 1974, John Schwarz and Joel Shirk discovered that among the vibrations of the strings there appeared a special particle with spin equal to 2, just like the graviton predicted by quantum gravity. With this discovery, string theory ceased to be a mere mathematical curiosity and emerged as the most promising candidate to unify all the fundamental forces of nature, including gravity. In 1984, Michael Green and John Schwarz managed to demonstrate that the theory is mathematically consistent only if spacetime has 10 dimensions, not 4. This discovery marked the beginning of a true revolution in theoretical physics. According to string theory, fundamental particles are not points but tiny vibrating strings, so small that they have dimensions comparable to the Planck length, about 10 to the power of 35 meters. 1,000 billion times smaller than an atom. Each vibrational mode of these strings corresponds to a different particle, like the strings of a musical instrument that produce different notes depending on how they vibrate. In this scenario, nature itself appears as a cosmic symphony in which strings dance in an invisible and mysterious space. The original theory, called bosonic, evolved into superstring theory, which also includes fermions, the particles that make up matter, thanks to a deep symmetry called supersymmetry, capable of uniting bosons and fermions in a single coherent structure. It's important not to confuse these tiny fundamental strings with the so-called cosmic strings, filaments of energy that extend over immense distances and which, according to some theories, would have formed immediately after the Big Bang. For a long time, it was thought that they were unstable, but today some physicists hypothesize that they could form a stable network that spans the entire cosmos, like an imperceptible cosmic web. The most astonishing part of string theory is its requirement for extra dimensions. In addition to the 3 dimensions of space and the dimension of time, the bosonic version predicts as many as 26, while the superstring version requires 10. Where are these dimensions hidden? The theory suggests that they are rolled up on themselves, so tiny as to escape any observational tool, much like a thread that from afar appears as a line but, when viewed up close, reveals its cylindrical structure. These inaccessible dimensions would be present everywhere, influencing the fundamental laws of physics without our awareness. In recent decades, physicists have learned to accept ideas that would once have been considered pure madness. Parallel universes, multiple realities, invisible dimensions. All that once seemed absurd is today the subject of serious and passionate research, and string theory is at the center of this cultural shift that is transforming our idea of the universe. The great obstacle remains the difficulty of verifying it experimentally. The extra dimensions are too small to be observed directly, and the energies required to probe the vibrations of the strings are enormously higher than those achievable with our accelerators. Yet, the mathematical beauty of the theory, its incredible internal consistency, and its ability to include all fundamental forces continue to make it one of the best candidates for a theory of everything, capable of unifying gravity with quantum mechanics. Some physicists even believe that string theory could explain the very birth of the universe, imagining a cosmos born from the collision of two membranes in an 11-dimensional multiverse. This scenario, known as M-theory, unifies the 5 versions of superstring theory into a single, more general framework, suggesting that these are not different theories, but rather different points of view on a single reality. Some researchers go even further, hypothesizing that the vibrations of strings could be the key not only to understanding matter and energy, but also to deciphering time itself, seen not as a linear dimension but as an emergence from the vibrational structure of the universe. There are even those who explore possible connections with consciousness, imagining that the deepest mental processes might have roots in the quantum dynamics of strings, opening new perspectives for theoretical and neurophysics. The idea that mass, charge, and spin are emergent properties of vibrations radically changes our way of seeing physics. There are no longer solid and immobile objects, but vibrational states in continuous transformation. If we ever manage to understand and control these primordial vibrations, we could manipulate matter itself, create new forms of energy, or even rethink gravity. The refined mathematical developments of string theory have already influenced fields such as algebraic geometry, topology, and number theory, demonstrating how theoretical physics can push beyond the boundaries of its own domain and open paths in the purest mathematics. Despite many aspects of this theory still being hypotheses, the fact that it manages to reconcile gravity with quantum mechanics, even if still incomplete, represents an achievement never reached before. In this journey among infinitesimal vibrations and hidden dimensions, string theory offers us a dizzying and breathtaking vision. The idea that everything we know is actually a harmonious symphony of invisible strings, dancing and creating the universe in which we live.